Okay, so next step, we are going to uh, take this idea of divisors and um, take it to the next level. So the next thing we might consider is what is the for two numbers, for any two numbers, what is the greatest common divisor? Now, as we've seen throughout the course so far, notation and terminology is not always 100% universal in math. So, sometimes it's called greatest common factor, sometimes it's called HCF, highest common factor. So, they're all mean the same thing. I grew up using greatest common divisor, so that's what we're going with. All right, so let's start by finding the greatest common divisor. Oh, and the abbreviation for that, we usually say GCD. It takes two numbers, so we write it as a binary function. We've talked about that before. So GCD of A and B, definition, I suppose, is the largest n, let's say, such that n divides A and n divides B. So that's what the greatest common divisor is. Easy enough. All right, so let's find the GCD. I'm going to switch to a different color. Let's find the GCD of 45 and 60. Okay, so without a better method at hand of doing this, let's just list the divisors. So divisors of 45. Okay, so we can do this. We got 1, and I'll put 45 out here. Okay, and then 2 doesn't go in. 3 does go in. 3 goes in how many times? 15 times. Okay, then let's see, 4 doesn't. 5 does. 5 goes in 9 times. Okay. Let's see here. 6 does not go in. 7 doesn't go in. 8 doesn't go in. And 9, we are actually already over here. So we're done because we've found the partner. Okay, so let me go ahead and collapse these guys. Ooh, there we go. Much nicer. Okay, so we'll do the same thing for the divisors of 60. We've got 1 and 60. We've got now 2 does go in. 2 goes in 30 times, and that means that 30 goes in 2 times. 3 goes in 20 times. And let's see here. Does 4 go in? Yes, 4 does go in. 4 goes in 15 times. That means 15 goes in 4 times. Does 5 go in? Yes, 5 does go in. 5 goes in 12 times. Let's see here. 6. Oh, we are running out of room. So smartboard to the rescue. Okay. Okay. So 6 goes in 10 times. Right. Now the 7 go in. No, it doesn't. Does 8 go in? No, it doesn't. Does 9 go in? Nope. And that's it. So 10. All right. So now all we have to do is we have to look on our list and look for the greatest common divisor. So we've got 1 and 1. That's good, but that's not the greatest. 3 and 3. Again, good, but not the greatest. 5 and 5. Maybe that's the greatest. 9. No, no 9. 15. Yes. How about 45? No. Okay, so the answer then is 15. So we have that the GCD of 45 and 60 is equal to 15. Awesome. All right. So let's keep going. Let's go back to this idea of divisors again. We'll revisit GCD in a little while, but let's go back to this idea of divisors again. So let's do another problem. Let's find the divisors of 2, 1, 4, 2. Now, we want to find the divisors of 2, 1, 4, 2. We could do it like we did before, just by trying a bunch of numbers, sort of, keeping track of them as we go. But this time, since this is a math for computer science course, let's think about this how we would have a computer do it. So computers are really good at doing something over and over again. And they do things very quickly. So one thing we might have the computer do is we might have, just if let's call this n, right? We might have the computer try the numbers from 1 to n. Okay, there's a lot of them. There's 2,142 of them in particular. So that's a lot. But for a computer, 2,142 is nothing. They can do thousands of calculations a second, so won't even take a fraction of a second. Easy enough. All right, but there's a slightly more efficient way to do it that you and I would probably use when we were trying to figure it out. And the fact of the matter is we don't need to actually try all these numbers, because anytime we find one that's on the lower end of the scale, it's going to have a partner on the higher end of the scale. If we go back and look at our numbers here, that's how we did it. We found 3 went in, and then we found out that 3 had a partner, 4, 1, 1, 5. So we did that just by knowing that 3 had a pair. 5 also had a partner, and then 15 also had a partner. All right. So let's see if we can exploit that idea of the partners to, to our advantage. All right. So n is our number. Well, in this case, n is 2, 1, 4, 2. But let's just do it symbolically. So n is our number. So let's say if a divides n, that means that there exists some b such that ab is equal to n, right? Okay, but if we divide by a, since we know that a divides n, we can just do that. So we know also that b is equal to b is equal to n over a also divides n. So there, for the price of 1, we got 2. And in particular, if we start with the smaller ones, we know that b is bigger than a. And furthermore, we know that if a is less than the square root of n, then b must be greater than the square root of n. All right, so in particular, we can just limit our search to trying numbers that are above or below above or below the square root of n, and since smaller numbers are invariably easier, we always start with numbers smaller than the square root of n. Okay, so 2, 1, 4, 2, let's see, what is the square root of that? And we're looking for integers, so we really don't have to be that exact about it. So if I bust out my trusty calculator and try this, I know that the square root of 2142 is approximately 46. All right. So all we have to do is try the numbers up to 46. A lot less than trying 2,142 numbers. And in fact, if we're going to do it by hand, we're going to do it. We're going to do it even more cleverly because we're only going to use the prime numbers. Now, to have a computer just use the prime numbers is probably more work than it's worth, because unless you're going to store a list, an exhaustive list of prime numbers up to the largest number that the computer can store, it's going to be more work than it's worth. So it's just easier to have it try all the numbers up to 46. So we start with 1. 1 obviously goes in. 1 has a partner 2, 1, 4, 2. Then you do 2. 2 goes in. It goes in. Let's see here. 1, 0, 7, 1 times. Oops, I'm missing a 1. Okay. Does 3 go in? Let's see here. Looks like it does. So we do 3. And we get 3's partner is 7, 1, 4. Okay. Let's see here. 4 does not go in, and we know that. Let's just real quick here. 2 goes in 1, 0, 7, 1. If 4 went in, 2 would have to go in again, which means this would have to be even, but it's odd. So no, doesn't go in. Okay. 5 doesn't go in. 6 does go in because 2 and 3 go in, so we can just divide by 6, and we get, let's see here, 3, 18, 19, 21, 34, that's going to be 5 times 42 is 357, okay, let's see here, does 7 go in? It looks like 7 does go in. 7 goes in 3, 0, 6 times, okay, how about 8? Well, if 4 doesn't go in, then 8 doesn't go in, so we'll skip 8. 3 goes in, so 9 might go in, and actually, in fact, it does. 9 goes in, let's see here, 2, that's 18, 19, 21, it's 34, so that's 3 times 27, 34, 72, and that is 8. 238, okay? Does 10 go in? 5 doesn't, so 10 doesn't. Does 11 go in? Nope. How about 12? 4 doesn't, so nope. 13 might go in. Check it. Nope, doesn't. 14, 2 and 7 do go in, so 14 definitely goes in. 14's partner is going to be 153. Let's see here, 15, nope, no 5, 16, nope, no 8, 17, we should try 17, turns out 17 does go in. I happen to have a list in front of me, so we're doing this a little quicker. 17's partner is going to be 126. Let's see here, 18. Well, 6 and 3 go in, so yes, 18 will go in. And 18's partner is going to be 119. Okay, we're getting there. 19, I'll just tell you, does not. 20 does not. 21, 2 and 3 and 7 do, so 21 does. And 21's partner is 102. Let's see here, and then let's see, skip a few. The next one turns out to be 34. 34's partner is 63. After that, we've got 42, and 42's partner is 51. And that's it. Alright, so there we were able to, again, kind of laboriously try to calculate the divisors of 2142. But again, the important fact here is that we use the square root of the number as sort of our reference point.